Okay, let's talk about first a little bit about the final. I sent out an email yesterday that had a kind of like a review. Did y'all get that? Yes?
It's the one that was in there, right?
Yeah, it was attached.
Yeah.
And then,
I think I printed out like the beginning of the semester. It's the same one.
oh, I don't know. I didn't look. And then there's, today I went through the book. I went through each of the chapter reviews, and I just kind of picked some problems, and I sent you a list of those problems. It's, again, just a guide to kind of go back and look at different topics. And we can talk a little bit more about the final, like how I see, like how many problems and how many of these types. We'll talk about that towards the end. But there's a few more things I want to discuss, okay? All right, so let's continue with that substitution. So what I'm going to do is I'm going to give you a problem here and see if you can come up with the substitution that we would use for this. Now, if you see it right away, don't shout it out, all right? Do not. I want everyone to have an opportunity to take a look at this. And the idea, remember, is to try and look for something within the integrand and then try to identify something that would be the derivative of that.
Do you want
right.
to just find you right now?
Yeah, just think about what it'll be, and then I'll ask you. Everyone have an opportunity? Think you have an idea of what u should be? What do you think u should be? X to the third power? Okay, so let me try that. If u is x to the third power, then what is the derivative of u with respect to x? 3x squared, right? No, it's okay. This is okay. Were you saying oh shit?
I said it was
oh shit. Why did you say that?
well because I didn't see that first book.
Okay.
It's off by the
You're off by a number. It is okay to be off by a number. Perfectly fine to be off by a number. And here's why. Because once I clear out this dx, I'm going to multiply both sides by dx. Then I have this expression, right? And if I kind of highlight the different elements of my integrand over there, I know that this x cubed, I will replace that with u, right? That's going to become a u up there. And the other remaining piece that I have not accounted for here is the x squared in the dx. And remember, this is multiplication. So if I wanted to rewrite this integral, I could have rewritten it like this. That's the same expression, right? And if I did it that way, I would still say that that's going to become u, and then this piece right here, x squared dx, I come back over to my work and I say, do I see x squared dx somewhere? Sure, right here. The problem is I have the 3. But because that's an equation, I can always work with the equation, right? And multiply both sides by the same thing, or divide by the same thing. So why don't I just divide both sides by 3? Or multiply by 1/3. I'm gonna write it like this. 1/3 du is x squared dx. And so now I have exactly x squared dx, which matches this exactly, right? Now, rewrite the entire integral. And what's going to happen is when I rewrite this, I'm going to convert it from an integral that had x in it to an integral that has u in it. So this becomes a new integral. E, right? E didn't go anywhere. E's still there. E to the what? U, because x cubed is u. And then x squared dx is actually going to become 1/3 du. times 1/3 du. And that's actually something I'm happy to see, because if I take that, remember with antiderivatives, constants come along for the ride, just like with derivatives they came along for the ride. I'm going to put the 1/3 out in front of the integral, because that's just going to be multiplication. And I'm going to ask myself, what is the antiderivative of e to the u, right? It's a new problem. The antiderivative of e to the u is e to the u plus a constant. But I have a 1/3 out there that's going to need to come with me. So at this point, the integral sign will go away, the du goes away. I just have the 1/3 e to the u plus a constant. And then the last step would be to substitute back in, what was u? X to the 3rd power plus c. This is the antiderivative of x squared e to the x cubed. Now, the way you could check your work is to take the derivative of this, right? If you take the derivative of this, you need to get that. So let's do it real quick. Cover up the 1/3. What's derivative of e to anything? Itself. Times the derivative of what's up here. What's the derivative of what's up there? 3x squared. So you're going to have 1/3 e to the x cubed times 3x squared. And the 3 and the 1/3 cancel. You get e to the x cubed times x squared, which is that. Make sense? All right, let's try another one. This one's going to be weird. Cosine of 5x plus 3 dx. Now, we all know that the antiderivative of cosine is what? The antiderivative of cosine is sine. Be careful with that, right? Because derivative of sine is cosine. That's a very common mistake for Cal 2 students in the beginning, is to think the antiderivative of cosine is negative sine. It's not, it's just sine. So you might think, okay, well, look, it's just the antiderivative is just sine of 5x plus 3. But it can't be. Think about that. If you thought that the answer to that is just this, well, take the derivative of it. What's derivative of sine of something? Cosine of the something? Times the derivative of what's inside, which is 5. And you don't have the 5 over there, do you? You don't. So somehow we need to get rid of that 5. So what do you think we're going to have to put out here? A 1/5. Now let's do it with substitution and see that we can come up with that 1/5 out there with the substitution. So do you see something in its derivative? Right? That's what I told you. You see something and its derivative. This one's a little weird. You're feeling like the u is 5x plus 3? Why could, I mean, you only have you have limited options here, right? It can be, you could pick just the 5x, you could pick the 5x plus 3, or you could pick the whole thing, cosine of 5x plus 3. The problem with picking the whole thing is that you would need to see its derivative there. And the derivative of cosine of 5x plus 3 is a big nasty thing, right? And it's not there. So 5x plus 3 looks like the best candidate. And I agree, it should work. Let's take a look at y. If we pick the whole thing, 5x plus 3, what's the derivative of this with respect to x? Just 5. Do you have a 5 there? Well, you actually have a 1, don't you? And you're off by a constant. I know that's weird, but I mean, that's true, right? You're off by a constant. All right, so now turn this into du equals what? 5 dx. And so now I'm going to play this little matching game. I know that my 5x plus 3 is going to be my u, right? So that's going to turn into a u. And the only other thing really that I need to deal with then is this dx, right? that dx to match up with that dx. So I need to get rid of the 5, so I multiply both sides by 1/5 or divide by 5. Yeah? So I get 1/5 du is dx. See it? And now I rewrite the problem. Any questions?
What would have happened if you just took like 5x? Does that change the whole thing?
Let's look at that after I finish this. All right? So let's see. This will become integral, right? Cosine didn't go anywhere. Cosine of what? U. The red part's u. And then dx is 1/5 du. I can take the 1/5 out of this integral, right? 1/5 is a constant. Cosine u du. Now the antiderivative of cosine of u is just sine u, isn't it? And you have the 1/5 out there. So this becomes 1/5 sine u plus c. But what was u? 5x plus 3. So this is 1/5 sine of 5x plus 3 plus c. That's our answer. And didn't we say that if we did, we thought maybe it might just be the sine of 5x plus 3, but we said no, it would be off by 5. We would need to come in with a 1/5. There it is. Got it? Okay, so the question has been posed. What would happen had I not chosen 5x plus 3 and instead chose just 5x? Well, du dx would be 5 still, wouldn't it? And du would be 5 dx, and I'd still be off by a constant, right? But let's see what happens when I rewrite the integral. When I rewrite this, I'm going to have integral cosine of what? What was u? 5x. So this is going to be u plus 3. You see that? And then what? 1/5 du. And then you can pull the 1/5 out. Like that. Now, you're not done. Because you're kind of back in the same situation. You're still trying to figure out what the antiderivative of this is, right? This whole thing. You have u plus 3 in there. You would need to do another substitution now.
Would you though? Because when you take the derivative or whatever, wouldn't it equal?
It would work this time, wouldn't it?
Times 1.
The only reason it's working is why?
Because it's a constant, right? The 3.
The 3 is not the reason it's going to work. Can anyone tell me why I'm not going to have to worry about like the 1/5 here, like I did here? Why do I not have to worry about that there?
Because of the power.
Not the power. The what?
Because the du dx would be 0.
Du dx would be 1,
Oh, yes.
wouldn't it? Look at it. If I see, I think what you're saying is this. I think you're saying, yeah, you can just go straight to this now. U plus 3 plus c.
Because when you do the whole thing.
Because when you take the derivative of the inside is 1, right?
Yeah.
Where back here, the derivative of the inside was what? 5. So if the coefficient of the variable is 1, then you're in business. But if it's something other than 1, you have to account for it. Now, I don't want to get too deep into this today. This is for Cal 2, and when you take Cal 2, you'll get into this in more depth. Like in my Cal 2 class, what I'll do is I'll introduce a problem like this, and then I'll say, all right, well, let's look at this in general. What if you have a linear expression in here? Start the whole problem over. What if the inside of that cosine function is linear? Right? Ax plus b is linear. So a and b are constants right now. What can you tell me about the antiderivative? Don't we already know it should be sine of ax plus b plus c? But not quite, because if I tell you to take the derivative of this, what are you going to get? Cosine of ax plus b times what? Times a, right? The number in front of x? You don't want that a to be there. So what would you put out in front of that? 1 over a. That's the antiderivative of that. Okay? So let's now, with that, that's kind of more like a formula. If I give you now, what's the antiderivative cosine of negative 4x plus 1 dx, the answer would be what? 1 over negative 4, or negative 1/4 sine negative 4x plus 1 plus c. See that? And what if it was the antiderivative of cosine of just x minus 10 dx? Then it's just sine of x minus 10 plus c. Because the a was 1, so you put a 1 over 1, it doesn't change anything. Make sense? And this would in fact work for just about every function. If you did, let's say, e raised to the ax plus b. Well, what's the antiderivative of e to anything? Should be itself, right? Should be e to the ax plus b plus a constant. But when you take the derivative of that, it'll be itself, and then the derivative of what's up there is going to be a, right? You don't want the a, so you'd put 1 over a out here. You see how you can start to come up with just a general idea for all these things? Okay. That's good enough. One more problem, and then we're going to move on to the last topic of the semester. Aren't you so excited? All right, last problem. X times x plus 4 to the 900th power dx. I just want to show you this one because it's enlightening. You can't distribute the x. You can't do that because order of operations. You would have to do the 900th power. So why don't you start expanding that? Okay? That'll be your take-home final. And you have to get every coefficient right. No. No, thank you. Right? You wouldn't want to do that. Theoretically, could you? Theoretically, you expand that out 900 times, right? 900 factors of it, multiply it all out, then distribute an x through, and that's just a bunch of powers of x, and you do them one by one, right? Okay, so that, no, thank you. So let's think about substitution. Do you see something in its derivative? X, the derivative of x would be 1, right? And we see a 1 there? Okay, my advice to you is to never, ever make a basic substitution of u is equal to x. And the reason why is because you're going to rewrite the problem. It's going to be exactly the same problem. Right? Because I'll replace this with, if I say u is x, this will be u, right? And then, so if u was x, then du dx is 1, and then that means du equals dx, right? And so I'll replace that with u, and that with du, and congratulations, you've just rewritten the problem in terms of u instead of x. That gets you nowhere though, right? So never make the basic substitution u is x. But I heard the other possible one, x plus 4. Yeah, let's just try it. I mean, look, it may work, it may not. U is x plus 4. What's the worst that could happen? We get stuck, right? Okay, let's try it. What's the derivative of this with respect to x? 1, and then that's just du is dx. Agreed? Rewrite the problem. I know I can replace this right here, right? That I can replace with u. I know I can replace dx with du, right? But what about that x out there? Not another substitution. Anyone see it? Anyone see what I can replace that x with? Where's my whip? Someone took it.
Whip?
Oh, my ruler.
Something with the 900.
Look at the new integral has to have u's in it. What? U minus 4. Where'd you get that from? Yeah, look at this equation up here. Don't we have an equation that relates u and x together? If I ask you to solve that for x, you would say u minus 4, wouldn't you? Right? Does that help us? Let's see if that helps us at all. I'm going to rewrite this. X is now what? U minus 4. And x plus 4 is now u. And so that's u to the what? 900th power. And then dx is du. Did that help us at all?
Maybe.
Absolutely, yes, it did. Can you distribute this u to the 900th through the parentheses now? Yes, you can. Because this thing, this binomial, is raised to the first power. The reason you couldn't distribute the x through is we had a binomial to the 900th power. You actually have to figure out what that is first. We have somewhat, in some weird way, we have switched the roles of the pieces in there, right? And so now, when I distribute through, I get u to the 901st power minus 4u to the 900th power. Right? I still have two terms in there? du. If you have two terms, can't you integrate each one of these term by term?
Yes.
Yes? And these are just power rules. That's like x to the 901. So what's the antiderivative of this? This would be, remember how we do this? 1 over 902 u to the 902. Okay, what about the next one? Minus 4 over 901 u to the 901 plus c. Yeah? What's u though? X plus 4. So our final result is 1 over 902 times x plus 4 to the 902 minus 4 over 901 times x plus 4 to the 901 plus c. I don't mind checking it. I don't mind checking it. Let's see. It's not going to be that bad. Take derivative of this. Chain rule, right? 902 comes down. You get x plus 4 to the 901, right? Over here, 901 comes down, minus 4 times x plus 4 to the 900, right? Factor out an x plus 4 from each of those. You have 900 factors of them here, right? And you have 900 factors of them here. So pull out x plus 4 to the 900, and what would you be left with? When you pull it out of here, what are you left with? X plus 4. And when you pull it out of here, what are you left with? A minus 4? 4's cancel. This is x times x plus 4 to 900. It worked. So the reason I wanted to show you that example is because here's an example of substitution where it wasn't as obvious as like the previous one where we did x cubed and the derivative was 3x squared. And it was very easy to see it right there. This is a substitution where, hey, look, you just got to try something, right? And see what happens. In this case, it works. Got it? So as I've told you before, in Cal 2, what we do is we spend a lot of the first couple of weeks. In fact, the entire first test is usually just all techniques of integration. So you have a couple of them. Basic substitution, which is what I'm talking about now. Basic substitution. Then you have integration by parts, is the next technique. Then you have trig integrals. Then you have trigonometric substitution. And then you have partial fraction decomposition. So there's 5 main methods for integration that we learn in Cal 2. What makes the test difficult, that first test, is that when you're given an integral, you are not told what method to use. So like as you're learning the methods and you're doing your homework, you're going to be working in this section. This section is called substitution. You know it's going to require substitution. Then when you get to the next section, integration by parts, you know that the problems that you're faced with are going to require that technique. And then each of the 5 different sections or techniques, you know while you're doing the homework what you're supposed to do. Then you get to the test. There's an integral and there's no prompting. And so you have to be able to identify the method. And it's that recognition of what to do is what causes a lot of the problems. If someone tells you, hey, here's an integral, use integration by parts, most people are going to get it. But the challenge is, can you get an integral without being told what method to use? All right? So, okay. Stay tuned. Take Cal 2. Is everyone here Cal 2? Did we vote last time? Who's not? This is it. Cal 1's the last. That's it? So you're the only one. Everyone else can go to Cal 2. All right. All right. So 11:26. Let's see. My goal is to try and be done by noon with this so that we can talk about the final. Let's see how this goes. All right. A goal that we have here is to find the area under a curve. So I'm going to draw a picture for you. Let's say you have a function. I will call this little f. And let's say we start at an endpoint A and we end at the endpoint B. And what I'm interested in is figuring out what the area below that curve is. All right, I want this area. It's going to be related to the antiderivative, all right? But I don't want you to think about that yet, all right? I want that area, understand? Yeah. Now, the reason why we would want to do something like this is if you think back in history, when we were trying to find areas of things, especially when it comes to like agriculture, and this is my land, that's your land, and where are, how much land do I have versus how much you have? The shapes that they have were never perfect shapes. We could find areas of rectangles very easily, length times width, we all agreed on that. And if you had some weird sort of, polygon looking thing and you wanted to find the area of that we could do also, because we could just split this up into triangles. You could just find a way to split this into triangles and find the area of each triangle. So for a long time, finding the areas of rectangles and polygons was, simple work, relatively speaking. But then you'd have some, some land that maybe ran across a river, and you said, okay, now I want to know how much land do I have? And this is not a polygon. Do you see kind of how this would tie in? So how do we find areas of irregular shapes that are not polygons? That's kind of the motivation of this. And even more, the Chinese were trying to figure out for a long, long time a very simple question. Well, it sounds simple. What's the area of a circle? We all sit here and say pi r squared. That's nice. We know that. It's true. But how did they determine the area of a circle back before the formula pi r squared was there? What they did is they used this thing called the method of exhaustion. And the idea is this. If someone gives me a circle, I can start to fill it with rectangles. And I can measure the area of those rectangles, right? And I start to try and fill this in. So I get a real nice circle drawn. I get a real nice ruler. I start drawing really nice rectangles. And I start adding up the areas of all those red ones. And I get some area, right? For all the red ones. But that would be too low, right? That would be below the true area. That's too low. So I'm going to say that's the lower area. Then what they would do is they would take a square and put it around the circle. That area is too big, right? And they would start drawing rectangles in here and subtracting these areas from that big square. And then what you get is an area that's too large, right? Too big? That would just be the difference though, right? So the true area of this circle, the true area is somewhere between those two, right? So when we say the method of exhaustion, what I mean is to get a better idea of what the true area was, they drew better rectangles, more precise, smaller, little thinner lead, and they tried to squeeze down the true area between two numbers. And they got pretty darn close. They got to the idea that the area was approximately 22 over 7 times the radius squared. So they got pretty close to pi. 22 over 7 is an approximation to pi. It's not 3.14, but it's close. All right? That's the best that they could do. All right? Then Newton comes along and says, wait a minute. Really, at the end of the day, what we're doing here is we're drawing a bunch of rectangles, right? And what I'd like to do is let the number of these rectangles go to infinity. If I could let these red rectangles, the number of them I have, go to infinity, that would approach, right? It's a limit. It would approach the true area. So Newton brought in his idea of the limit and was able to actually nail down the exact area. Make sense? So let's go back over here to this idea of trying to find the area below this, all right? Newton said this. Newton said, all right, what I'm going to do is I'm going to take your picture here and I'm going to approximate the area, just like the Chinese did with all those rectangles. And he decided, I'm going to cut this picture up into some sections. So let me draw. I'm going to take this number line. Here's A, here's B. I'm going to cut it, let's say, into, and I don't know how far I want to push y'all right now, but let's see if you can handle this. Newton said, I'm going to cut this into n equal sections. So maybe n is 10, so it would be 10 equal sections, or maybe just 4 sections. I'm just going to say n sections. Is that all right? So you've got one section here, one section here, one section here, and there's a bunch of them in here, right? They all have the same width to them. And then, wherever that point is, wherever those points are on the number line, he's going to take those and plug those values into the function and get a y coordinate for each of those, right? And then he's just from that first y coordinate, from this one right here, he's just going to draw a rectangle. And then draw another rectangle, another rectangle, another rectangle, another rectangle, another rectangle, and keep doing this for all of them, right? And do you see how this would be a good approximation? And Newton had no problem adding up the area of rectangles. I mean, we all know the area of a rectangle is the width times the height, or length times height, or length times width, however you want to say it. Yeah? Agreed? And so this would be an approximation. How could he get a better approximation? More rectangles, right? The more rectangles I have, the better my approximation is going to be. Do you agree with that? And if there was a way to let the number of rectangles go to infinity, I should converge down to that true area. Yeah? All right. So you understand the concept, right? The basic idea here? Yeah? Okay. Now I'm going to try and do this. I don't know how this is going to go. All right. I want to look at this picture again. I want to focus on this number line. Here's A. I'm going to call that A x naught, x sub 0. That's my initial x coordinate. The next point, I'm going to call x sub 1. The next one, x sub 2, x sub 3. And then I'll have all of these, and I'll go all the way down to my last one, x sub n, and that's B. So what I'm talking about here are these blue points right here, okay? Yes? Yeah? Okay, I'm just giving them numbers. And then my function is up here doing whatever the heck it's doing. All right. And I want us to talk about the area of a rectangle. So I'm going to pick a point in between these two right now. This is very important, all right? I'm going to pick a point in between these two, and I'm going to call that point x1 with the tilde over it, just so you know it's not the same as this x1. So x1 with the tilde is between these two. And right now, please understand that I'm giving you a preview into Cal 2, but this is not like this is what you're going to be doing in Cal 2. This is to try and get you to understand why the antiderivative works for finding. We're going to use the antiderivative to find this area, but my explanation here is going to hopefully convince you as to why. All right, so you got it? I've got x sub 0's here, x sub 1's here, and I've picked a point, x sub 1 tilde is in between those two. Yeah? All right, now from that point, I want us to go up to the function. That's just whatever the function's height is right there, right? And I'm going to draw a rectangle. It's going to come out to the left a little bit. It's going to come out to the right a little bit and hit the two edges of x0 and x1. Do y'all see that rectangle right there? What is the area of that rectangle? What's the area of that red rectangle? Okay, it's x sub 1 minus x sub 0. That's how wide it is, right? Everyone agree with that? So that's your width. How tall is it? It's the y coordinate there, isn't it? It's this height, but isn't that height this number plugged into the function? Yes? So I'm going to say f of x sub 1 tilde times that. Does everyone agree that that's the area of that first rectangle? Sure? Any question? No? Yes? No? Yes?
How do you do the width thing?
Okay, let me give you a number line over here. Let's say this was 1, 2, 3, and I picked a point in here, whatever it is, that's my x1 tilde, and I drew a rectangle. How wide is this rectangle? Look at it. How wide is that? How wide is this? 1 unit, right? Isn't it? From here to here? You can get that by doing 2 minus 1. Right? 2 minus 1 would be the width. Let's change it. What if that went from 1 to 4? How wide is this? 3, right? So what I'm doing here is to find the width of this, I'm taking the x coordinate here and I'm subtracting the x coordinate here. That's how wide it is. Yeah? Okay? Let's repeat. Let's pick another point in between here. Let's call that x sub 2 tilde. And tell me what the area of this one would be. So I go up, and then I draw a rectangle out and over like that. So what's the height what's the area of that rectangle? X sub 2. Now I'm going to add it to this area, because that's the area of the first one, right? The area of the next one is x sub 2 tilde times, how wide is it? X sub 2 minus x sub 1. You following? Then I'd have another one. Yeah? What would the next one be?
The f of x sub 3
Tilde
times x sub 3 minus
x sub 2 dot dot dot, right? I keep going. What would the very last one be? So that would be, I'd be picking my last one right here. That'd be x sub n tilde, right? So we would have f of x sub n tilde times, what's the last ones? That's kind of hard. Wouldn't it be x sub n, that's the last point, minus x sub whatever n minus 1 is, right? The one right before it. So if this was like x sub 100, this would be x sub 99. So does everyone agree with me, or does anyone disagree with me, that this sum of red things would be an approximation to the area? That's an approximation to the area? Okay. Good, good. I want to also point something out. All of these what? Yes? They're all the same, aren't they? Because I said we're going to cut it into n equal pieces. So the width of all these are all the same. So let's give them a nice little symbol. How about I call them delta x? Because isn't that truly just the change in x? That's just my change in x. As I move from one rectangle to the next, it's how much my x changes by each time. Yes? All right, we're getting there. But now I need to kind of blow your mind a little bit. Everyone got this? Put it on the back burner for just a second. I need to remind you of something. We're almost there, though. I'm pretty excited. Recall MVT. What was that? Mean value theorem. The mean value theorem said if you have a function f and it's continuous on a, b, and f is differentiable on the inside of it, then there exists a c in AB such that the following is true. F prime of C equals F of B minus F of A over B minus A. Okay, that's the mean value theorem. Right? And what it meant geometrically was this. Back when we were looking at this, said, look, if we have a function that goes from here to here, then if we connect the two endpoints with a secant line, somewhere in there, I should have a tangent line that runs parallel, right? That's what this says. But that's actually not how I'm going to use it. I'm not even going to look at the geometry of it. I just want to look at this equation with you for a second, all right? Look at this equation carefully. I would like to rewrite it, just in a slight change. You all ready for the change? I'm going to change this to capital F. And I'm going to change that to capital F. Then how would this change? This is capital F. This is capital F. Right? And what is the derivative of capital F? Remember when I defined it with integration, we said that capital F is called an antiderivative of little f if f prime, capital F prime. No? Do y'all remember me putting this up? We said if capital F prime equals little f, then capital F was called the antiderivative. So what can I replace this with right here? Instead of f prime, just little f. Understand? That's just different notation for the same damn formula. I'm using capital F here, and instead of putting capital F prime here, I'm putting little f, because little f is the derivative of capital F. That okay? Yes? Yes. Okay, I'm going to do one more thing to this formula. I'm going to multiply both sides by b minus a. And remember, b minus a, back in the picture, a was this endpoint and b was that endpoint, right? So if I rewrite the mean value theorem, then this becomes f of c times b minus a is equal to capital F of b minus capital F of a. I need y'all to see that. Is that all right with you? Just multiply both sides by b minus a.
What are we doing?
Just do you agree? Yes? Okay. So let's just recap real quick. If you have a function, right, and you evaluate it at c, and remember, c was inside a and b, wasn't it? And then you multiply that times the difference of the two endpoints. That should be equal to the antiderivative of this function evaluated at the endpoint b minus the antiderivative of it evaluated at a. So anytime I see this, right, if I ever see this, I can replace it with this. As long as this c lives in between b and a. So can I come back to the red now?
Sure.
All right. Do you see this right here? I can rewrite that with the mean value theorem. Does this x1 tilde live in between these 2 points? Yes, it does, right? So this should turn into what? Capital F of, not b. Remember, a and b are the two endpoints. What are our two endpoints here? x1 and x0. So shouldn't this be capital F of x1 minus capital F of x0? Do y'all see that? Y'all sure? Which, now the next one, I'm running out of room. I'm going to put them up here. This is where I am. I'm capital F of x1 minus capital F of x0. That's the first one. Plus, now the next one. Same thing, mean value theorem on this. Does x2 tilde live in between those two? Yes, the mean value theorem says then just evaluate the antiderivative at the two endpoints. So that should be capital F of x1 minus capital F of, I got those backwards. x2 first, x1 here. The a and the b is the right endpoint, a is the left endpoint. Still with me? Keep going. Plus, what's the next one? This one right here? Capital F of x3 minus capital F of x2. And I keep doing that, right? Keep doing it. Plus dot, 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 until I get to the very last one. The very last one's going to be capital F of x sub n, right? Minus capital F of x sub n minus 1. Do you see anything that cancels? I do. Okay, this first one right here, I'm going to kind of break these up into groups. These were the groups, right? I have like one group, two group, three group, and then down there. So this first one here is getting killed off by this one, right? Then this first one is being killed off by that one. Then this first one should be killed off by one down there, shouldn't it? With me? And then we keep going. Now this is the first one, isn't it, in this group? It would be killed off by one down here, but there is nothing down there. So this one remains, doesn't it? This one, what about, does this one go away? It cancels with the one that was in front of it. Yeah? What's left? The only thing left is this and this, right? Those are the only two things left? So that is, let me write the positive one first. Isn't that all equal to f of x sub n minus f of x sub 0? What is x sub n? B. What is x sub 0? A. That means that if I want to know the area below this curve, all I need to know is the antiderivative and then plug in the two endpoints to the antiderivative, and I have the area. Unfrickin' believable. The mean value theorem has to be used to do that. Well, they didn't have the limit. They weren't using the limit, and that took a while to develop. There's a lot of subtleties here. Look, continuity, you have to have a continuous function. You have to understand what differentiability is. Mean value theorem was the piece that they were missing. But the mean value theorem only comes from a thorough understanding of differentiability and continuity. And so, all right. Wow, incredible. Now, there's a little subtlety here that's kind of lost, all right? And I don't know if I think I snuck it by you. The sum, if we add up all these rectangles, wasn't that an approximation, right? So what we need to do is we need to let this delta x get smaller and smaller, right? If we make these smaller, then they're going to become more narrow, right? Which will get us better and better and better approximations. So what we do is we let this delta x, we let the delta x go to 0. We take a limit. So technically speaking, the true area, see if you can follow this. The true area under this curve, which I called A earlier, the true area is something like this. It's a sum, right? Think you've seen that notation before? I'm going to be doing something like f of x sub something, let's just say I tilde times, well, this thing over here was, what did we call that piece right here? It was the same for all of them, so what do we call it? Delta x, right? Isn't this the area of each of the rectangles? And what I'm going to do is I'm going to do first x of f of x sub 1 tilde, then 2, then 3, and add all these up, right? So I'm going to let that I start at 1 and stop at n. If you've never seen sigma notation, don't freak out. But this just means add up a bunch of stuff, start with I being 1, stop when you get to n. And then what I'm going to do is in front of this, very important part, I'm going to let n go to infinity. And what happens when n goes to infinity is this sum becomes infinite, right? And this number right here goes to 0. And what happens when you take this limit is you get this f of b minus f of a. This thing works. And so we have a notation for it. This is a sum, right? This is a function. This is a little tiny little x, right? Why don't we just use the integral sign to represent this limit of the sum? This right here, why don't we just put f of x there? And this piece right here, since it's infinitesimally going to 0, why don't we just call that dx a differential? And that is your integral. Understand? This is a summation of the height of a function times its width. That's what that is. Now, we're going to add some more elements to this now. And then, hey, I'm going to make it till noon. This is going to be great. So all of that was just so I can put the following on the board, all right? If you didn't follow any of that, then don't worry about it, okay? Because I'm just going to give you a formula now. This is called the definite integral and the evaluation theorem. First, let's start with notation. So this left side, I'm just going to put notation. All right. When we write this f of x dx, then this is equal to capital F of x plus c. What this means is when you see this notation, it's telling you, hey, everyone, find the antiderivative of this, please. Right? That's what that's saying? And then you do, and you add c. Yeah? This is called the indefinite integral. Because all it gives you as an answer is a function plus a constant. All right? That's different from this next thing where our notation is going to change, which is integral f of x dx. All that's the same, right? But now what I'm going to do is down here, I'm going to put an a, and up here I'm going to put a b. This is called the definite integral. And this definite integral gives you the area under f between a and b. So if you want the little picture under, that goes with this, that area underneath in here, right? That area, this is the way we would write that.
And that simply just states that when you get the antiderivative, you're going to plug A.
Yeah, I'm going to show you. Yes, there's a way we do it. Okay, just need a couple of more things, notation-wise, and some things. What was this thing called again? Integral sign, right? That's the integral sign. This right here is called the integrand. This right here was just the differential, all right? Now we've added these two things right here, which we know, like visually, these are the two endpoints, right? But we have names for these also. This is called the lower limit of integration. And what do you think the one on top is called?
The bigger.
The bigger. Yeah. The upper. I was going to say something smart-ass too. I'm glad you beat me to it. Upper limit of integration. So, most of the time when someone asks you to evaluate a definite integral, your answer is going to be a number. Most of the time. Because it's the area underneath the curve. All right? As opposed to a definite integral where your answer is a function plus c. Totally different concepts, yes? All right. So I think it's time for us to do an example, but I'm going to put the formula up here and then use it. So just write this down right now. Evaluation theorem. The definite integral is equal to, just write this down, okay? Capital F of x with this bar to the right of it like this, a, b, which is equal to capital F of b minus capital F of a. Just write that down, and I'll show you how I'm going to use that in just a second. Okay, I just said that, well, I kind of, in some very loose form, proved to you that in order to find the area underneath a curve, we just need to find the antiderivative and then evaluate at the two endpoints, right? So it's kind of a two-step process. You first find the antiderivative, and then you plug in the endpoints. So when I write the evaluation theorem this way, what we're going to do is we're going to start with the original problem. We're going to find the antiderivative first. And we're going to draw a bar and put the two numbers that we have here. Then on the next step, we're going to actually plug the two numbers into the antiderivative. All right? So what I'd like to do to start is I'd like to find the area under f of x equals x on the interval 0 to 6.